Apache Kafka explained. Imagine you're starting a business with just one system generating data, a simple source system that sends information to a single target system. Life is easy, data flows smoothly, and everything just works. But as time goes on, your company grows. You add more systems, more applications, more services, more databases. Suddenly, your once simple data pipeline turns into a tangled mess. Every source system needs to communicate with multiple target systems, and they all use different formats, protocols, and schedules. The complexity skyrockets. This is where Apache Kafka comes to the rescue. Kafka is an open source event streaming platform that decouples source and target systems, making data exchange seamless and scalable. Instead of systems talking directly to each other, they all communicate through Kafka. Kafka can ingest and process a wide range of event-driven data, including website activity, financial transactions, real-time pricing updates, GPS coordinates, and more. Once ingested, this data can be efficiently routed to various downstream systems, such as databases, messaging services, analytics platforms, auditing systems, and more, ensuring reliable and scalable event-driven architectures. When reading from or writing to Apache Kafka, data is processed as events. Each Kafka event consists of several components: a key, a value, a timestamp, headers, and an associated partition, which we will explore shortly. For instance, in an e-commerce scenario, we can have customer 101 as a key. For value, we can have an action such as added milk to the cart. We can have a timestamp, which records when the event occurred. For headers, we have metadata, such as specifying the data format, and we can have an associated partition of 3. Messages, including their key and values, can be represented in various formats. The most commonly used formats are string, JSON, protobuf, and Avro. Kafka messages are stored in a Kafka topic as serialized byte arrays. Before publishing a message, a Kafka producer serializes the data into a byte array format, ensuring efficient transmission and storage. When a Kafka consumer reads from the topic, it deserializes the message back into its original structure for processing. Before you can publish messages onto Kafka, you first need to create a Kafka topic. For example, we can have different topics like topic A, topic B, and topic C in what we call a Kafka cluster. A topic in Kafka is like a category or channel where messages are stored and organized. Think of it as a mailbox where multiple producers can drop off messages and multiple consumers can pick them up. The great thing about topics is that they support multi-producer and multi-consumer models. This means multiple services with producers can write messages to the same topic, and multiple services with consumers can read from it, all without interfering with each other. Unlike traditional messaging systems, where messages are deleted after being consumed, Kafka retains messages for a configurable amount of time. You can specify how long Kafka should keep messages by setting different retention policies for different topics. This makes Kafka perfect for event-driven architectures and replaying past data when needed. Kafka topics are divided into partitions to enable scalability, parallel processing, and fault tolerance. Each partition is stored on a Kafka broker, which is a server responsible for managing and storing data within a Kafka cluster. Instead of storing all messages in a single location, Kafka splits topic data across multiple partitions, allowing producers and consumers to produce data in parallel. Each partition acts as an ordered, immutable sequence of messages, where new messages are appended to the end. Every message within a partition is assigned a unique offset, which represents its position in the log. A topic can be spread along multiple Kafka brokers, but a partition always belongs to one broker. For example, you can scale a Kafka topic to 9 partitions distributed across 3 Kafka brokers. This ensures that the message processing is not limited by the I/O capacity of a single broker. If you need to handle millions of messages per second, Kafka can easily manage this by increasing the number of partitions and consumers. More partitions allow for higher throughput by enabling multiple consumers to read messages in parallel. In many cases, it's best to match the number of consumer instances to the number of partitions for optimal performance. In our example, since we have 9 partitions, we might want to scale our application to 9 consumer instances, ensuring each partition is processed separately without conflicts. When a new message is published to a Kafka topic, it gets assigned to one of its partitions. If the message has a key, like a customer ID for example, Kafka ensures that all messages with the same key always goes to the same partition. And Kafka ensures that any consumer reading from that partition will always receive messages in the exact order they were published. Another key feature of Kafka is its ability to replicate partitions across multiple brokers. In production, the best practice is to set the replication factor to 3. When a producer writes to a specific broker and partition, Kafka automatically replicates the data to the 2 other brokers. You should also keep in mind that both the producer and consumer write to and consumes from the partition leader. If a broker hosting the leader fails, Kafka's controller detects the failure and promotes one of the in-sync replicas to become the new leader. It then seamlessly redirects the producers and consumers to the new leader, ensuring continuity with minimal disruptions. So let's say you have 6 partitions and a replication factor of 3. That means Kafka will create a total of 18 partitions, distributing them across multiple brokers. This setup ensures fault tolerance and high availability, so even if a failure occurs, you can continue reading and writing data seamlessly without any disruption. So now let's take a look into producers. Kafka producers are responsible for publishing events to Kafka topics. When a producer sends an event, Kafka determines which partition it should go to based on the partitioning strategy. If a key is provided, Kafka uses a hashing function to consistently assign events with the same key to the same partition. If no key is provided, Kafka distributes events in a round-robin fashion for load balancing. Once an event reaches a partition, it is stored in an ordered immutable log, ensuring durability and sequential reads. Producers can also configure acknowledgements to control reliability, choosing whether to wait for confirmation from one, some, or all replicas before considering an event successfully written. Kafka consumers, also known as subscribers or readers, are responsible for reading events from Kafka topics. They subscribe to one or more topics and pull data from assigned partitions in the order that they were generated. Kafka maintains consumer offsets, which tracks the last read position in a partition, so that it can stop and restart without losing its place, ensuring reliable processing. Consumers read from topics as part of a consumer group, and a group can only consist of one consumer, which enables scalable processing. Kafka dynamically assigns partitions among consumers in the group, ensuring that each partition is processed by only one consumer at a time. This setup enables parallel processing and scalability. If a consumer fails, Kafka automatically redistributes its partitions to the remaining consumers in the group, maintaining fault tolerance and uninterrupted data consumption. If you enjoyed this video and found it helpful, don't forget to like, subscribe, and leave a comment below. Thanks for watching, and I'll catch you in the next one. Bye for now.